All right, so last section we're going to look at this week is section 3.5. So it's similar to what we did the past couple days. We're still going to look at synthetic division. We're still going to use rational root theorem, except sometimes you might get imaginary answers. So first thing what I'll do is just quickly review imaginary numbers just to make sure we're good with that. All right, so remember the idea that if you have a number that is a zero of a function, that means you plug it into the function and you get 0 for y. That's what it means to be a 0. Okay, another way of saying it, and we've already said this before, is that it's an x-intercept. Okay, and there's also other ways to say it, like x minus the root is a factor, but for now I don't want you to worry about that. So if a polynomial doesn't cross the x-axis, it doesn't mean that there aren't roots. Every equation has roots. It just means that the roots aren't real. Okay, so the graphing calculator can only visually show you real roots. If a problem has roots that are not real, the only way to find them is with algebra. Okay, the calculator can't really help us too much with imaginary roots. And how could you get an imaginary root? If you had something like this. And I asked you, where does that parabola cross the x-axis? It doesn't. Okay, so if it doesn't cross the x-axis, there aren't going to be any real numbers that are roots. Here's an example of an equation. Actually, that equation could be that picture. It's a parabola shifted up 1. There's no number that you can square and then add 1 to and ever get 0. Because anytime you take a number and square it, at the smallest it can ever come out to is 0. That's it. You can never get a negative when you square something. So if you take a number that's at least 0 or higher and add 1, you're never going to get 0. So there's no real answer to this problem. But if we try to solve it, set it equal to 0, and subtract 1 from each side, you get negative 1 equals x squared, and then you'd have to take a square root. Now on your calculator, if you try to take the square root of a negative, it's not going to work. Okay? If you type that, usually you get an error. Okay? Because square root of negative number is what kind of answer? It's not real, it's imaginary. Okay? So you can't take the square root of negative 1. So, if we want to be able to solve something like that, then we have to come up with a way to represent that. And does anybody know the symbol or the letter that we use to represent the square root of negative 1?
It's like an I.
Yeah, it's an I. Right? So I is the square root of negative 1. It's just the symbol that we use. And if you ask, well, why do we use that symbol? I can't really explain why. There is no reason why. It's kind of like in geometry if you said, can you explain to me why parallel lines don't cross? No, I can't. Because the fact that parallel lines don't cross, it's a definition. That's just the way we define it. Parallel lines never cross. End of discussion. You can use that fact to figure out other things. But that's exactly what this is. It's a definition. I represents the number square root negative 1. It's just a symbol. But remember, it's not, even though it's a letter in the English alphabet, well, that's a letter in the Greek alphabet. But in math, it really stands for a number. It's 3.14. Okay. I is a letter in the English alphabet. But in math, it stands for the number that I just circled. Okay, so remember, it's really representing a number. It's not a variable. That's the point. So if you took the square root of negative 1 and squared it, what happens when you square and square root something?
Becomes
They cancel out. So the square and the square root cancel. And what are you left with? You're left with -1. Okay, and that's important. So anytime we get a I squared in a problem, anywhere, we always want to change I squared to -1. And you might be like, what about I cubed or anything else? We don't have to really worry about anything else. I squared is the only one we got to worry about. So let's take a look at what happens if we plug I into the equation we just had on the other page. So I plug in I and I square it, and we add 1. What did we just say I squared is? -1. Plus 1. And what's -1 plus 1? 0. So what does that mean about I? It's the what of this equation? Or at least one of the what? It's one of the solutions, and we call the solution when it's equal to 0 a root. Okay, it's a root or a 0. So I is one of the answers to this equation. It's one of the roots. If I is an answer, then there's also another answer. Okay, because your exponent tells you how many answers there are. There's 2. Right now, we're not going to talk about the other. Any questions on that? Okay, so now, I kind of showed you where I comes up. It comes up when you take the square root of negatives. Now we'll look at a really quick review of complex numbers. In order to do the kind of stuff we did yesterday, what you really need to know about complex numbers is how do you add, subtract, multiply, and divide. All right, so first of all, how do you write a complex number? Okay. Complex numbers are written just like I have on the right there, A plus BI. The idea is A is the real part, B is the imaginary part. Now, not every single number you ever use in math has a real and an imaginary part. Like the number 5. It's a complex number, but you can think of it as not having an imaginary part. Think of the imaginary part as 0. Okay, so technically, every number you've ever studied for anything you've ever done in math is a complex number. It's just a lot of times the imaginary part is 0. If it's 0, we usually don't write it. Okay, these are all examples of complex numbers. Okay, 4, it's a complex number without an imaginary part. 3i, okay, that's just the opposite. That's a complex number without a real part. Think of it like this. In 3i, the real part is 0. The imaginary part is 3. -7i, same idea. Okay, here's a complex number that has both parts. The real part is 2. Imaginary part is 3. Okay, and here's another example. Real part 2/5. Just because there's no number in front of I doesn't mean there isn't one there. If there ever isn't a number, pretend it's a 1. Okay. Just like with variables, even though I is not a variable. With variables, we do the same thing. Okay. Any question on that? Yeah?
Why is 4 a complex number again?
Everything's a complex number.
Oh, okay.
Yeah, everything is. Sometimes it doesn't have an imaginary part and 4 doesn't.
Okay.
So think of complex numbers as like the biggest category, like Earth. Okay? That covers everything. Okay? We all live on Earth somewhere. Okay? And then under that, you got your more specific categories. Complex numbers is like the whole thing. Back to the beginning. All right. So when we do arithmetic with complex numbers, I'm going to give you just a few general kind of guidelines. You can think of an I as a letter. So like if you had a problem like 2x plus 3x. What's 2x plus 3x? 5x. Well, if it was 2i plus 3i, you would hope it would be 5i, and it is. Okay, so when you're combining like terms, even though I is not a variable like x is, you can think of I the same way. 1i plus 5i is 6i. When we multiply, we end up using the double distributive property, or FOIL. Okay, so just to kind of show you what that'll look like, I'm going to come right back to it. But when we do multiply, basically going to do something like that. And when you do out the FOIL, you're going to end up with some I squareds. Okay? Anywhere that you get an I squared, don't leave it as I squared. Change it to -1. Okay, for division, when we get to that, we're going to have to use the idea of what's called a conjugate. Okay, so I'll show you what a conjugate is first, and then I'll show you how you use it. And then the last thing is, how do you simplify square roots with negatives? Okay, so let's look at an example. Okay, square root of -x. X could be anything. Square root of -5, -12, any number. What number is in front of the x, even though it's not written?
1.
1, or in this case with the sign, it's a -1. Yep. So you could think of what I have on the left really like that. It's the square root of -1 times x. And now when you have a square root, you're allowed to take each part of it and separate it into its own roots. So the square root of -1 and the square root of x separate. Well, one of those things we just talked about. What's the square root of -1? Just I. Right? If we go back for a second, the square root of -1 is just I. Okay. So this part can be written as just I. So basically what happens when you take a square root of a negative, you pull an I out in front of the square root. Okay. So when you have a square root, generally, let's say you took like the square root of -3, you'd write it like that. How come you wouldn't want to write it like that?
Isn't the -1 still under the square root sign?
What does it look like is under the square root?
The -1, the I.
The I, yeah. So to me, if you put it like that, it's kind of iffy. It kind of looks like the I is under it. I can't really tell. Like, should this line have really stopped here? That's a little clearer. But if we just want to avoid that, write it like that. Put the I in front. Now, if you don't have a square root, it's perfectly fine to put the I after, because there's no confusion, right? There's no root there that it could be under. So for I, it's perfectly fine to write. We usually don't put I for. Okay? Only time we put the I in front is when you have a root. All right, let's try a couple examples. When you simplify square roots of negatives, you don't have to go through every step. If you can just write the final answer, that's fine. Anyone think they could tell me what the square root of -4 would be?
I square root 4.
Yeah, it would be I square root. I'm just going to put that over here for a second. I square root 4. And then what's the square root of 4? 2. So it's I times 2. We just write 2I. It's okay to put the I after because I took the root and it came out nice. So there's no root left. Ezekiel, how about the square root of -9? 3i. 3i. How about square root of negative 7? Yeah?
I and the square root of 7?
Yeah, this time you can't take the square root of 7. So you just write it as I square root 7. And the last one, square root of 20. Negative 20. So this one you do the same way you would do as if it were square root 20. Simplify the square root of 20 first. And then when you're done, just put an I in front of your answer. Okay, so how would the square root of negative 20 simplify? Casey?
4 square root.
So I agree. Let's just go off to the side for a second. So if you were going to simplify that, it would be the square root of 4 times the square root of 5. But then what's the square root of 4? 2. So the square root of 20 is 2 root 5. So what about the square root of negative 20?
2 square root of 5?
Yeah, we would do 2i square root of 5. Okay, it's okay to put the I after the 2, but it's still before the root, so there's no confusion if the I should be under the root or not under the root. Okay, so any question on simplifying square roots? All right, so now I'll go through one each of add, subtract, multiply, and then divide. Okay, when you are adding two complex numbers, basically think of it as combining like terms. Combine the real part with the other real part, and by combine, in this problem, I mean add. And then combine the imaginary part with the other imaginary part. And again, by combine, the symbol is add. So, let's start with our real parts. Caitlin, what do I get if I combine 7 and 4? Yeah, we're going to get, what'd you say again? Well, I remember you're adding.
Adding?
Yeah.
It would be 11.
Yes. This is not a distributive property. If you put a plus sign or a minus sign between them, don't do distributive property. That's only for a problem like that. Now you do distributive property. Okay, so 7 plus 4 gives me 11. And how about, Dave, what's negative 3i plus 5i?
Negative 3i plus 5i is 2i.
2i. Okay, so that's 11 plus 2i. And that's it. That's how you add complex numbers. Let's look at subtract. Subtract is the same idea. Okay, combine the real part with the other real part and the imaginary with the imaginary. But remember, this minus applies to both. You're not just subtracting the 6. You're also subtracting the I. Okay, so Andrew, what would be my real part if I do 4 minus 6? That's my real part. And yep, you want to do the imaginary part too?
Yeah.
All right, so it's negative 2i minus I.
Negative 3i.
Yes. Okay, so remember on subtraction, subtract both. Any question on subtraction? Okay, and normally if I was teaching this, before pre-calculus, we might practice 3 or 4 adding and 3 or 4 subtracting, and we might even stop there and not even do multiplication on the same day. But hopefully that's pretty much reviewed. All right, now let's look at multiplication. All right, multiplication. 2 plus 3i times 5 minus I. This is where you use distributive property. All right, so Josh, can you tell me, I already drew it out, but what would be the first 2 things you would multiply?
2 and 5 and 2 and the I.
Yep, so 2 times 5.
Which is 10.
Yep, and then 2 and what's the other thing?
the -1.
Negative
I.
I, yeah. So I'll try to make my 1's like this and my i's like that. So 2 times negative I, what's that?
-2I.
Negative 2I. Okay, now let's do the inner. Gabby, what's 3I times 5?
15i.
15I. And now the last part, let's look at it in a couple steps. It's a positive 3I times a negative. AJ, what's a positive times a negative? Negative. Okay, so we handled the sign. Now we have a 3I times I. Ezekiel, what's 3I times I?
3I squared.
Yes, 3I squared. Okay, there's a few things we gotta do there. First thing I would do is combine like terms. Michael, what's negative 2I plus 15I?
13I.
Yep, 13I. Now, anything I want to do with that last term? We talked about that. There's something there we should fix. Yep.
Plus 3.
Sorry. Yeah, go ahead.
Yeah, would it be plus 3?
Yeah, what's going to happen is it's minus 3. But remember, I squared is a negative 1.
Wouldn't it be plus 13i?
Yeah, thank you. Plus 13i. So now you have a negative 3 times negative 1, which is what Mina just said. Positive 3. And now you can combine positive 10 with positive 3, and what do you get?
13 plus 13i.
Yeah. Just a coincidence that the real part and imaginary part both came out with it. That doesn't have to happen. Okay, so that's how you multiply. Okay, any questions on multiplying? Okay, so last thing, and then we'll get into the kind of stuff we were doing yesterday, is dividing. In order to divide complex numbers, basically the goal is when you have division, you never want to leave an I. Let me show you an example of something that's not good. You never want to leave an I in the bottom. So that's not a good way to leave a final answer. Just like we can't leave square roots in the bottom, we can't leave I in the bottom. So, there's got to be a way to get rid of I. Okay, and there is. The way you get rid of the I is to use what's called the conjugate. So all the conjugate means to do is change the sign, or a short way to say that is negate. Change the sign of the imaginary part. So if your original number was A plus BI, the conjugate is A minus BI. You don't do anything to the real part. Just change the sign of the imaginary part. Okay, so let's just practice a couple of those. If you had 3 plus 2i, what would be the conjugate of 3 plus 2i?
3 minus 2.
3 minus 2. Yep. What if you had 4 minus 5i? Yeah.
4 plus 5i?
Yeah, it would be 4 plus 5i. What if you just had 3i?
Negative 3i.
Negative 3i. If that one seems a little confusing, think of 3i like this. It has no real part. The conjugate of 0 plus 3i is 0 minus 3i. And that's what we just wrote. What's the conjugate of 6? 6 stays the same. You're like, well, wait, why don't you change the sign? Think of 6 like this. 6 plus no imaginary part. The conjugate is 6 minus 0i. Plus 0 minus 0, same thing. So any question on how you find a conjugate? Okay, so last thing, then we'll get into some roots in a second. In order to divide two complex numbers, the first thing you have to do is look at the bottom and find the conjugate. And then you're going to multiply the numerator and denominator by the conjugate of what's in the bottom. Okay, don't do the conjugate of what's in the top. That won't help. It's the conjugate of what's in the bottom. Okay, so multiply the numerator and denominator by the conjugate of what's in the bottom. So Ian, can you tell me what the conjugate is of what is in the bottom?
2 plus 3i.
Perfect, 2 plus 3i. So I'm going to multiply the bottom and the top by 2 plus 3i. So what this really turns into is just multiplication. But you got to do it twice, on the top and the bottom. I'm going to do the bottom first, and I want you to watch what happens. Okay, those bottom terms are almost the same except for the sign. So something kind of nice is going to happen. So we start with 2 times 2. Miley, what's 2 times 2? So we get 4. And then I have 2 times 3i. What's 2 times 3i?
-6.
positive 2 times positive 3i? 6i. Right? What's positive 2 times negative 3i? So what's going to happen with the 6i and negative 6i? They cancel out. So whenever you multiply conjugates, you don't need to worry about doing the outer and the inner. They cancel every time. If you want to write down plus 6i minus 6i, you can. Then it just crosses out. The last part doesn't. Negative times positive is negative.
9i squared.
Negative 9i squared. Okay, we'll come back to that in a second. But if you start to look at it carefully, you should see that in a minute, there's not going to be any i's left in the bottom. So we've done what we needed to do in the bottom. In the top, you just have to multiply it like usual. 5 times 2? 10. Then we've got 15i plus 2 more. 17i. And let's see if we can do this all at once. We have I times 3i. It's 3i squared, which is really the number negative 3. It's 3 times negative 1. Okay, is that good? Is everything simplified there?
Do you want to change I squared?
Yeah, definitely want to change the I squared. I want to do that. And I'm going to do 10 minus 3 in the top. Okay, 10 minus 3 gives me 7 plus 17i. And let's just fix it right here. What is 9i squared? What number?
Plus 9. Minus 9.
Right. So 9i squared is a minus 9. That minus in front is still there.
Positive.
So now it becomes 4 plus 9. Any question on why the bottom is 13?
You add 9 to 4.
Yeah, you just add 9 and 4. Yep. And now that's basically the final answer, except what they usually do is they separate it into the real part, which is 7/13, and the imaginary part, 17/13. Okay, so in that last step, just put each number separately over that. Okay. That's standard form. You can put the I in the middle, or you could put the I in the top. Most of the time when it's a fraction, people just put I in the middle. Okay. All right, any questions on division? All right, so now that we've practiced a little bit with the basics with complex numbers, let's just look at some problems where we find the roots. And now if we get a complex answer, we should know a little bit more about how to deal with it. Okay, so find the zeros. Andrew, are all the x's already on one side? Yeah, then we're good to go. Fill in 0 for y. And solve. And what kind of equation is this? Yeah, it's quadratic. And how can you solve a quadratic equation?
Factoring.
You can factor if it works. Don't think factoring is going to work on this one. So what else can you do?
Graphing.
You could graph. The only problem is going to be if the roots are imaginary, the calculator won't show them. But it would show the real roots. So that's absolutely perfect if you're finding real roots. What else can we do? We can do quadratic formula. Kelvin, what's A, B, and C here?
1, 1, and 1.
Yeah, they're all 1.
Yes.
So not very interesting, but they are all 1. And we're going to get negative b plus or minus the square root of b squared minus 4 times a times c. So it's just 4 times 1 times 1. And what do we divide by? 2a, which is 2 times 1? 2. Okay, so get negative 1 plus or minus, what's 4 times 1 times 1?
Negative 4.
Yeah, it's just negative 4, and what's 1 minus 4? Negative 3. Okay, now do we leave the answer with the negative under the root? No, what do we pull out from that? An I. So your final answer is negative 1 plus or minus I root 3 over 2. Okay, and there is really no other way to get that answer. The calculator can't help you at all with that. Okay, any questions on how we got our answers here? Okay, keep that in mind. A was 1, B was 1, and C was 1. It's gonna pop up again. Okay, I'm gonna have that pop up in another problem because then we've already done all the work to solve. Okay, so we'll come back to this. If you look at the answers you just got, okay, let's go back and look at them. Negative 1 plus I root 3 over 2, negative 1 minus I root 3 over 2. What's it called when all you do is change the sign of the imaginary?
Reciprocal.
That's when you flip. It's the conjugate, right? Those two answers are conjugates. Negative 1 plus I root 3, negative 1 minus I root 3, both over 2. So the fact that you just got conjugates there, that's not a like a lucky kind of thing. That always happens. So anytime that you solve for the roots, complex roots always occur in pairs. So if there's one root, there's automatically another one. And the nice thing is you don't have to figure out the other one. The other one is the conjugate. So if I had a problem and I told you 3 plus I is a root, what do you automatically know is also a root?
3 minus.
3 minus.
What was the last time?
It was 3 plus I.
3 minus that.
3 minus I. If 3 plus I is a root, 3 minus I is automatically a root. This only works when the imaginary part isn't 0. Because if the imaginary part was 0, then you don't even have an imaginary number. All right. Okay. So complex roots always occur in pairs. So that means, could you ever have 3 complex roots to a problem? If you've got 3, then you must have You must have 4. Okay, you never get an odd amount of complex roots. Okay, so all the theorems that we've used so far, remainder theorem, factor theorem, synthetic division, rational root theorem, everything still works with complex numbers. All right, so what I want to show is that 1 minus 2i is a root of, can't really see it, x cubed plus x plus 10. Okay, so I'm going to ask the same question I've done before. If 1 minus 2i is a root, what else do you know? Okay, yep, you do know that, so that's something different. 1 plus 2i is a root. But if 1 minus 2i is a 0, what would be a factor? X minus it. If something is a root, x minus it is always a factor. So what I'm going to do with synthetic division is I'm going to divide by what comes after the minus sign, just like we always do. And when I do the synthetic division, I'm going to hope that I get a remainder of 0. So we're going to put 1 minus 2i on the outside. And notice this one's a cubic. Okay, I probably wouldn't go any higher than cubic with synthetic division with a complex number because it starts to get kind of time consuming. Okay, the example in the book is a 4th degree. I wouldn't give you one that high. Okay, this would be the highest. So we've got 1, 0, 1, 10. Okay, what do we do with the first number? Bring it down. So that step's not too bad. And then we're going to multiply 1 minus 2i times 1. Okay, well that's not bad. Just distribute the 1 to each thing. Does it change anything? No. So when we multiply, we get 1 minus 2i. And now what do we do with that column? We add it. We're adding it with 0, so there's nothing to add. All right? And now we have to multiply again. 1 minus 2i times 1 minus 2i. And I'm going to put the answer right there. So it doesn't get messy in the problem. I'm going to do this off to the side. 1 minus 2i times 1 minus 2i. Okay, so when we go through it, 1 times 1. What's 1 times negative 2i? Yeah, and then another 1 times negative 2i gives you negative 4i. And then let's try to do this part all at once. Negative times negative, positive. And then what's 2i? I erased part of it. What's 2i times 2i?
4i squared.
Yep, so we have a positive 4i squared. But what's I squared? So it's negative 1 times 4, which is really minus 4. If you don't want to do that, you want to write out every single step, that's fine. I'm just trying to save a little writing. And then 1 minus 4 gives me negative 3 minus 4i. So that's probably going to be the worst calculation we have to do in this whole thing. The next step is easy. Add. There's never anything to add with the imaginary. So that stays the same. What's 1 plus negative 3? Negative 2. And now somehow I'm going to hope I get a negative 10 and that all the i's just disappear. Because if I get a negative 10, then I add it, I get a 0 remainder. That was the goal. Okay, so our last multiplication is this times that. So I'll do that off to the side. 1 minus 2i times negative 2 minus 4i. Right. Colin, what's 1 times negative 2?
-2.
Yep, negative 2. Hannah, 1 times negative 4i.
Negative 4i.
So that's a negative 4i. I'm just going to put that here for a second. And then what's negative 2i times negative 2?
4i.
Positive 4i. I got a negative 4i, positive 4i. So what happens there?
Cancel.
They're gone. So all I'm left with is negative times negative is a positive. 2i times 4i, that's 8i squared. But what's I squared?
Negative 1.
And what's negative 1 times 8? And what's negative 2 take away 8?
Negative 10.
Negative 10. So I get a remainder of 0. So we just showed that 1 minus 2i is a root doing synthetic division. And now you get kind of the bonus. If 1 minus 2i is a root, so is 1 plus 2i. You wouldn't have to show that. All right, so a little bit harder just because you have to do the foiling twice. But again, you'd never have to do it more than twice in a problem. Any question on that one? And I'm not saying you're going to have to do this on every single problem. The one we just did before it, all you had to use was quadratic formula. You didn't have to use synthetic division at all. Okay, so this doesn't always come up. Okay, how come an odd degree polynomial will always have at least one real root? No matter what, always. Yeah?
One side goes down, one side goes up.
Right. Odd polynomials, one side goes down forever, one side goes up forever, and it's connected. Well, if you go up forever and down forever, you're going to go through the x-axis sometime. You have to. Okay, so we've kind of already mentioned that. Okay, so let's find all the zeros of x cubed minus 1. And a hint is anytime I give you something higher than quadratic, it's going to have to cross the x-axis at a nice number. If it didn't, you couldn't solve it. Okay, so there's going to be a number that's a nice number where this crosses the x-axis. In order to find it, we'll make a list of possibilities. Okay, so P, so all the factors of my constant. How about, Braden, what are the factors of my constant here?
Is the constant x3?
No, that's a variable.
Is it -1 then?
Negative 1.
So wouldn't it be 1?
And?
-1?
Negative 1. So the factors of my constant are 1 and -1. What's my leading coefficient? So same thing, 1. So the factors are also 1 and -1. So my possible rational roots, bless you. What are all the different combinations you could have if you take all the p's and divide by all the q's? It's just plus or minus 1. So I guarantee you this graph is going to cross the x-axis either at 1 or -1. How can we figure out which one it is? Yeah, we can just graph it. All right, let's graph it. X cubed minus 1. Now I'm looking between -10 and 10. I really don't even need to look that far. Just focus between -1 and 1. Somewhere right in there. Okay, which one does it look like?
1.
Yeah, looks like 1. So now that we know 1 is a root, I can write that down as one of the answers. Find all the zeros. 1. And we'll get 2 other ones. You always have to have as many answers as the highest exponent. So we'll have 2 more. Now, since, well, when you saw the graph, how many times did it cross the x-axis? Just once. So what does that mean about the other 2 roots? They're imaginary. Okay? So in order to get the other 2 roots, you have to turn that cubic into a quadratic. So what do I do with that 1 to turn that cubic into a quadratic? Or what did we do yesterday? Once you have a root, what's the last thing we need to use? And once you do this, it's going to turn the cubic into a quadratic.
Turn the 1 into a factor.
Okay, so if 1 is a root, x minus 1 is a factor, and then what do we normally do with the x minus 1? What operation? Now we do synthetic division. Yep. So put the root on the outside. You're going to divide through by it. This time, make sure you put 0 in for your x squared and x. And this should be really quick to go through synthetic division. 1 times 1.
1.
And 0 plus 1.
1.
1 times 1.
1.
0 plus 1. And then 1 times 1 again is 1. Negative 1 plus 1. That's my remainder. We already knew it would come out to 0 because we checked it on the calculator. So now I have a quadratic. That's A. That's B. That's C. So now you need to solve this. Does that look familiar at all? How come?
But it's another quadratic equation. Well,
It is a quadratic equation, but what looks familiar about it? Yeah?
That's the same answer as before.
Yeah, we just solved this problem. X squared plus x plus 1, we did right here. X squared plus x plus 1. So we've already gone through all the work to solve that part of it. So those are your other 2 roots. Negative 1 plus or minus I root 3 over 2. So put that right here. And that's it. So that's generally the process. Anytime you have a cubic or anything higher, you got to find one root at a nice spot, divide through by it. You'll take your equation that was a degree 3, and then it'll turn it into a degree 2. Then you can use quadratic formula. Again, if you didn't have a nice root you could find on the calculator, you would be stuck. So every problem on the test has to have a nice root. Questions on those zeros? Roots. Same. Okay, so you might have noticed, and I already pointed it out, highest exponent is a 3, 3 answers. Highest exponent on this problem was a 2, 2 answers. So the pattern is that the total number of roots, so the total number of answers you get, equals the highest degree, or the degree of the polynomial. So if you had a degree 8, you're looking for 8 answers. Most of the ones I give you are either like degree 2 or degree 3. And whenever we mention something having to do with roots, we could also mention something having to do with factors. Because if a degree 3 has 3 roots, then a degree 3 has 3 factors. And that's what this says. If you had a problem with 4 roots, then you have a problem with 4 factors. You always have the same number of roots and factors because they're the same thing. So like this problem. What's the degree of that example? Tell me.
What?
What's the degree of that?
Oh, 3.
3. So if you were to factor that, how many factors would you expect? 3. And that's exactly what you get. X plus 1, x plus 2, x minus 3. Now, looking at the factors, you should also be able to tell me the roots. What would be the root of the first factor? -1. How about the second factor? -2. And the third factor? 3. So if you know the factors, you know the roots, automatic. Roots don't have to be distinct. Just because a root is repeated doesn't mean you ignore it. It's still an answer. Like in this problem, the root -1 is repeated twice. The root 2 is repeated 3 times. So there are 5 answers to this problem right here. It's just some of the answers repeat. And there's a couple ways you can describe how it repeats. You can say -1 is a double root, and 2 is a triple root. Or you can say -1 is a root of multiplicity 2. That just means it's a double root. It occurs twice. 2 is a root, or a 0, of multiplicity 3, because it occurs 3 times. If there's 5 factors here, if you FOILed all this out, what would be your highest exponent? If you did all that out, what would be your highest exponent?
2.
It would be higher than 2. If I just FOILed out the first 2, I would have a 2. But if I kept going and then FOILed that with the third one, the fourth one, and the fifth one,
At least.
my exponent, my highest exponent, would be a 5. There might be some other exponents in there too, like some 1s and other ones, but the highest one would be a 5.
Wait, so how many roots does that have?
This problem has 5 roots.
But they're all the same. So
Well, 2 of them are the same.
2.
And then, so -1, the roots, if you were going to list them, are -1, -1, 2, 2, 2.
Okay.
Those are the 5 roots.
So if you were to like boil all that together and put it in a graph calculator, then it would just be like looping.
Yep, if you FOILed all that out and put it in a graphing calculator, it would look, it would just go up and down a couple times. But it would only cross the x-axis twice.
Okay.
It would cross the x-axis at -1 and cross again at +2. Now, if you made all these numbers different, like x plus 1, x plus 2, x plus 3, x plus 4, x plus 5, then you would get something that looks like this. 1, 2, 3, 4, 5 distinct answers. Okay, this one wouldn't look like that because it doesn't cross 5 times. It only crosses twice. Any question on that? Okay, so that's it for the stuff today. Homework is on page 193. And some things that you want to know how to do for the test tomorrow. You definitely want to know how to find roots. They could be real or imaginary. Real or imaginary. You also want to know how to do long division. So, long division. Synthetic division. What else? How to find the remainder quickly. So we talked about the remainder theorem. Rational root theorem, that's a big one. There's like 5 or 6 questions on that. Because with the rational root theorem, usually you do it in 3 parts. List all the possibilities. Narrow down the list of candidates, and then find the actual answer. Okay. I think that's pretty much everything that's on the test.
No, no.